Our next simple gas law is Avogadro's law. Yes, it's the same Avogadro from Avogadro's number. So what this gas law tells us is that as the number of moles of gas increase, we're also going to see an increase in the volume of the gas. The opposite holds true because it's a direct relationship. They go in the same direction. So we could say as the number of moles of gas decreases, we're going to see a decrease in the volume of the gas. The moles of gas in the mathematical relationship is symbolized by the letter N. The units of moles has to be moles, right? But once again, your volume can take on any units as long as they match between V1 and V2. Like all of these gas laws, I think they have a lot of analogous situations in day-to-day life. So if you get more space, you move into a bigger place, right? Most likely you're going to accumulate more stuff. Or if you get more stuff, you're probably going to need more space to hold that stuff. So I always like to think of Avogadro's law as being more space, more stuff. The constants here are going to be temperature and pressure. While we're studying the relationship between volume and moles of gas, we want to hold temperature and pressure unchanging. Next, we need to discuss what's known as the combined gas law. This allows us to study changes in pressure, volume, and temperature all at once. The classic example of the combined gas law is known as the egg in the bottle demonstration. So how you do this, you would get a hard-boiled egg and peel it. And then you're going to throw maybe a small piece of lit paper or a matchstick into the bottle. So you have a little combustion reaction going on, which in turn is heating the gas molecules inside that bottle. They're moving around. They're going to escape. So this is what I'm trying to symbolize by those green arrows. You're going to see the egg vibrate a little bit. Why I wrote higher temperature, greater volume. Remember, volume is increasing, and that's why we're seeing the gases escape. So eventually, even though some gases is getting out, we're not replacing the oxygen in there. So eventually the combustion reaction is going to run out of oxygen and extinguish itself. At that point, the gas in the bottle starts to cool and they stop moving as quickly. Their kinetic energies decrease. So two things will happen. Volume will decrease because remember, gases will shrink as they cool, and pressure also decreases inside the bottle. On the outside of the bottle, though, the pressure is still at 1 atm. So it creates a very dramatic suctioning of the egg inside the bottle because there's a very low pressure and smaller volume present inside the bottle, and then it's feeling the regular 1 atm of pressure on the outside. It just draws that egg right in. In terms of units, pressure and volume just have to match. So if you're doing atmospheres on the left, do atmospheres on the right, or milliliters and milliliters for volume, whatever you want. Temperature has to be in Kelvin. That's going to be really strict. Alrighty, so if you turn to number 9, we're going to do an example of the combined gas laws. I always start these the same. As I'm reading through the problem, I like to label each of the values. So 500 liters sounds like a volume, given that, it's liters, of a gas is prepared at 700 millimeters of mercury. So I just learned that millimeters of mercury is the pressure unit. So I'll put P1 there, and 200 degrees Celsius, that'll be my T1. The gas is placed into a tank under high pressure, okay, when the tank cools to 20 degrees Celsius. So sounds like we have a second temperature here. The pressure of the gas is 30 atmospheres, so we have a P2. What is the volume of the gas? So we must be solving for V2, since we already have a V1, right? Now that we got everything labeled, we do have to worry about units a little bit. You'll notice that our P1 and our P2 don't match. We got millimeters of mercury on one and atmospheres on the other. So I converted, and you could do it either way, but I chose to convert the 700 millimeters of mercury to atmospheres. So this is actually going to be my P1 when I set this up here in a second. I'll ignore this because I've already converted it. Temperature has to be in kelvins. So I have my T2 and my T1 right there, and we're all set. Alrighty, so now that I got everything organized, I can start plugging stuff in. I wrote my combined gas law down here. Not a big fan of the fractions, so before I really get started, I'm going to cross multiply and get this into a single line. So I'm going to have P1 V1 T2 equals P2 V2 T1. Now there's quite a bit to plug in here. Let's see, we got P1, which is this 0.9210526 atmospheres. Our first volume, which is 500 liters. And T2, which is the 293.15 Kelvin. All of that is going to equal P2, which is 30 atmospheres. V2, I don't know. I'm going to put that more towards the end. The order doesn't matter, right, when you're multiplying. Let me get T1 in there. So 473.15 Kelvin. I'm almost running out of space here. Let me put V2 in a more vibrant color. So V2 is our unknown. And so we can do this, even though it takes a second to set up, we can do all of this in one step in our calculator. So I'm going to open my parentheses, multiply all this, and then I'm going to divide. I'm going to open up parentheses again, and I'm going to bring over the 30 atmospheres times the 473.15 kelvins, and I'm going to close my parentheses. So I'm dividing on both sides by the 30 times the 473.15. So it's going to go away on that side, leaving me with just V2. Let's check the units. So atmospheres will cancel with atmospheres, and Kelvin will cancel Kelvin, and we're just left with liters, which is perfect. At the end of the day, our new volume is going to be 9.51 liters. And I left it at 3 sig figs because of the 30 atmospheres. The ideal gas law is where it all comes together. PV equals nRT. The new part here is the gas constant R. On your sheet, it's written as 0.0821. I'll typically write 0.08206 because that's the way I memorized it. Same difference there, it just depends on how many sig figs you want out of your final answer. The important thing with the R value though are those units. So it's liters times atmospheres divided by moles times Kelvin. If you look in the reference or in the back of a textbook, you're going to find other versions of R with different units. We're not going to use those. They have different applications. We're going to focus on this version that has the 0.08206 or 1, whatever you want, but with these units. Why? Because over here, we need the units of the ideal gas law, the values that we plug in, to match. So our pressure needs to be in atmospheres. Our volume needs to be in liters. Moles is moles, right? And then our temperature needs to be in Kelvin, as always. Alrighty, we're going to go through this ideal gas law problem. But what I want to emphasize here a little bit is the fact that we're not going to know it's an ideal gas law problem when we start. So we're reading through this. Calculate the volume. All right, so it sounds like they want us to solve for volume. So potentially we would label this V1 of 6 moles. All right, this must be my N1. Maybe it's an Avogadro's law problem. Again, if we didn't know at first. 6 moles of carbon monoxide gas at 305 Kelvin. Let's do a T1 here. And the 1 atmosphere, I'm going to call P1. So when you run into this scenario where you only have one set of variables, you don't have a P2 or a V2 or an N2, that's a big tip-off that this is an ideal gas law problem. Because the ideal gas law doesn't have the subscripts, right? So since I've labeled everything and I've decided that I'm going to use the ideal gas law, it's just a plug and chug at this point. So I wrote in my pressure, I'm solving for volume, and I have the 6 moles times the gas constant times the temperature of 305 Kelvin. I need to isolate volume, so I'm going to divide each side by 1 atmosphere. In this case, it's not going to be huge because anything divided by 1 is itself, but if it was any other number, these parentheses around the top are critical. So open parentheses, throw in all the values, close your parentheses, and then divide by your pressure. Always check the units. So atmospheres will cancel with atmospheres, moles with moles, Kelvin with Kelvin, and we're left with liters, which is perfect because we're trying to figure out the volume. So the volume equals 150 liters. I do have 3 sig figs, like across the board. So I'm going to put a period here, or we could just use scientific notation, 1.50 times 10 to the second liters. The last thing we need to talk about before we jump into a bunch of problems is this conversion factor. It says that 1 mole of an ideal gas is going to take up 22.4 liters of space. Like all conversion factors, it can be flipped. So we can also say that 22.4 liters of our ideal gas corresponds to 1 mole of that gas. Why is there a picture of a box? I used to have a colleague, he found it, a 22.4 liter box. I mean, I believed him. And so it's a really cool visual to think, wow, if I have a mole of oxygen, it would take up this much space. I still need to find this box for myself, right? But for now, I would encourage you all to think about 22 hydro flasks, right? Most people's hydro flask is 1 liter. Or if you drink 2-liter sodas, think about 11 of those soda bottles lined up. That will get you to 22. And that's gonna give you an idea of what does 1 mole of oxygen gas look like in terms of the amount of space. So what is an ideal gas? Well, honestly, there's no such thing. Just like you'll never find the ideal man or the ideal woman, we're never going to find an ideal gas. However, everything, the ideal gas law and all our simple gas laws, this conversion factor, they're pretty decent approximations. That begs the question, why don't we have ideal gases? Well, ideal gases, the atoms of the gas would have no volume or negligible volume. And how's that possible? Even our smallest gases like hydrogen or helium, we know that those atoms are going to take up some kind of space. So that's not going to work out. The other issue is that ideal gases don't exhibit intermolecular forces. They can't be attracted to one another. And in the real world, that's not true either. The gas particles will interact with one another and be attracted to one another. So there's some issues or some things that'll never happen with the ideal gas law, but the take-home message is that it does work out pretty decently most of the time. It's a fair approximation for what we need. So problem number 7 is about Kevin Durant, the basketball player. We're told that he has a mass of 109 kilograms and his lungs hold about 7 liters of air. Part A asks us, how many moles of air are in Kevin Durant's lungs? It also tells us, I didn't write it down, that we can assume that the air inside his lungs acts like an ideal gas. That's important because it allows us to use the conversion factor we just talked about. So we know that 1 mole of an ideal gas takes up 22.4 liters of space. So this is basically a conversion problem. We're going to start with the volume of his lungs. And since I want to get rid of liters, I'm going to put it in the bottom and I want to go to moles. So I'm going to say 1 mole has 22.4 liters. Liters will cancel with liters. And when I do 7 divided by 22.4, I get 0.3125 moles. However, since we're only given the volume of his lungs to 1 sig fig, we really can only report this to 1 sig fig. So let's do 0.3 moles. Part B of the Kevin Durant problem. We're asked to calculate how many moles of gas are in his lungs after he exhales. We're also given this conversion factor that when somebody exhales, they typically will breathe out about 6 mils of air per 1 kilogram of their body weight. So I'm going to start with that and figure out what kind of volume of air are we talking about here when he breathes out. So I'll start with the mass, 109 kilograms. And the conversion factor said for every 1 kilogram, a person's going to breathe out about 6 mils. So in my calculator, I need to do 109 times 6, and that's going to leave me with units of milliliters. I actually am thinking maybe I want to change this to liters, right? And we can see if one of the simple gas laws will apply. So I'll do 1,000 milliliters in 1 liter. Get your answer, divide by 1,000. That left me with 0.654 liters. So given the answer in part A, we don't necessarily have to use that conversion factor again. So here's what I'm thinking. The previous answer, I can call that N1. And the previous question told us that he typically has 7 liters of air in his lungs. Let me call that V1. This is how much he's breathing out. The problem is calculate the moles of gas kind of remaining in his lungs. At least that's what it sounds like from the wording. So I'm going to do 7 liters minus 0.654 liters because he's breathing out that gas. That leaves me with 6.346 liters. I can call that V2. And if you think of another way to solve this, I'm already thinking there's probably a couple different ways to solve this. Go ahead and try it. See if it's going to work out. Alrighty, since I have V2, all that leaves me to solve for is N2. So I can use Avogadro's law, more space, more stuff. V1 over N1 equals V2 over N2. If I cross multiply, that's going to simplify to V1 times N2 equals V2 times N1. Now I'm going to plug and chug. I'm missing information about N2. So V1 was 7 liters. N2 is unknown. V2 is 6.346 liters. N1, we just got in the previous problem, 0.3125 moles. I want to isolate N2, so I'm going to divide each side by 7 liters. When I plug this in the calculator, I want to use a big set of parentheses. So I have 6.346 times 0.3125 divided by 7. And that gives me 0.283. What are my units? Liters cancel with liters, and I'm just left with moles. Perfectly reasonable result, because we would expect the moles to go down when he breathes out, right?